Last video, we saw the debate between Newton and Bishop Berkeley over the vanishing term in Newton's calculation of rate of change. Berkeley's argument that you cannot divide by zero was correct. Newton's argument was wrong, even though he was correct in the example of the rate of change of x squared with respect to x being equal to 2p at x equals p. In what follows, let's imagine there's a court where we're going to decide the correctness of the argument. You will play three roles. In the first role, you will be the lawyer for Newton. In the second role, you will be the lawyer for Berkeley. And finally, you will be the judge, not delivering a verdict, but convincing yourself about the correctness of the argument. And in the process, you will meet three new concepts you need. If you know how to analyze this argument, you can use the same process to analyze any argument. And as you do that more often, you will become a better mathematician. So let's get started. Let's start as the lawyer for Newton. We will start with y equals x squared at x equals p plus o and compute the difference, which we call dy, with y equals x squared when x equals p. Berkeley's team agrees that this equals 2op plus o squared. Further, they agree that the change in x, dx, is just o. And they also agree that dy by dx at x equals p is 2op plus o squared divided by o. And so far, we have common ground. Now, we will pick a small o, not 0, and set dy by dx equal to 2p plus o. Any objections? None, says Berkeley's lawyer. I'm going to pick a non-zero o so I can divide, and let's say o equals negative 0.0001, and I'll claim that dy by dx is 2p, and I'm only ignoring something that's incorrect by 0.0001. Objection, as Berkeley's lawyer, you say, 0.0001 is still way too big. Now, as Newton's lawyer, you play your first great argument. You call on Berkeley's lawyer to pick any non-zero threshold that they think is an acceptable difference between 2p plus o and 2p. Berkeley's lawyer says, I want the error to be less than 9 zeros after a decimal point and then followed by 1. No problem, you say, and you pick o equals to the decimal point followed by 10 zeros and then 1. O is not 0, so you can divide to get dy by dx equals 2p plus an error that's smaller than the threshold that Berkeley's lawyer just picked. Berkeley's lawyer says, I want the error to be less than 30 zeros after a decimal point and then followed by 7. No problem, you say, and you pick O equals 31 zeros after a decimal point and followed by 1. O is not 0, so you can still divide and get dy by dx equals 2p plus the really small term that you are ignoring, which is smaller than the threshold that Berkeley's lawyer just picked. At this point, Berkeley's lawyer should realize that the genius of the opposing side's argument is that no matter how small the threshold he picks, the opposition can pick a value of O not equal to 0 and claim dy by dx is 2p and an error smaller than his choice. Being a smart judge, you conclude that with these new arguments, Newton is correct about the rate of change of x squared at x equals p is indeed 2p, and so does Berkeley's lawyer. But before conceding the case completely, Berkeley's lawyer objects. He says, this may well be true for the function y equals x squared, but what, for example, if the function behaves discontinuously around a neighborhood? Then you can no longer claim that the error will be small. In this picture, it's hard to define what the rate of change of the function at x equals x naught is. To make Newton's argument correct for that case, we need two more concepts, continuity and differentiability. We will get to that next. Image credits, all images via Wikipedia.